Welcome back. This is the last chapter on how to set up neural networks, and we want to introduce a nonlinear principle of localization, which is very important in getting contrast on picturing the world. So, and I would say this is a fold. Last chapter we had on the cut. This is very similar on the fold. So let's have a look and an example. So again, we have this kind of data. This, for example, is there's a certain salary, there's a family size, and the question is buying a car or not. So you observed these samples, family size, budget, buying a new car. So this is the data set. Take that. So, and you see in the graphics here, this is clear, this is clear, here it is folded, non-linear, some complicate things. So now let's have a look how neural networks, linear layers, work on this data. What is the behavior? Now we have a linear network. They cannot match this fold. So this is how we can do this. The network looks like this. So we have 2 dimensions, 1 scalar, 2 goes to 4, 4 goes to 2, softmax for the classes 0 or 1, by or not by. Yeah, this is therefore we have a softmax and we have the class 0 and 1. So we don't want to have intermediate things. So this is our network started. And look it up. Now we train it. All the same, all the time the same. We train it. And it's going like this. Error rate, you see it's not funny. Yeah. So if we go for the graphics of the result, we ask here for the probabilities of the network. We can, for example, can ask, this is how it is done. Data, we don't have a validation set because very few data. Just take the one. Data of 1. Probabilities. We need a one. Okay. Then he says probability 89%, it's a 0, and probability 1 is it's 12%. So if we take that as gray level, so take this as gray level, make then a disk as a graphics, and so all this is detail, you can try to get it out. It looks like this. So you see it's smoothing it out in a certain line. Even if there are some here, you have 8, 12, another, so it's some 30 parameters. So they can't make the differences because they have a linearity always means within the absolute and with the logic of time. So, and this corresponds to this Euclidean or Cartesian system, this view, which means you have this bird's eye view, and if things move, their distance keeps the same. If they rotate, the distance keeps the same. So therefore you are in an abstract, absolute space. Quite different from the hyperbolic space, which is this. So then you take a certain position, and then you have the proportion depending on the distance to your subjective position. So everything is always kind of rotating. The whole coordinate system is a kind of rotating wherever you, which kind of position you take. So, and this is what aliens do. So they don't take this linear perspective, they take a non-linear hyperbolic system, as you know from these drawings from illustrations of, for example, M.C. Escher. So, if you put that to a linear thing, as we had it with the ramp, this is the learning curve, and this is called the logistic sigmoid, and this looks like this. So you take a certain position, and depending on the distance, the things get another proportion, depending on your position. So you have high resolution here, and very low resolution the farther it's away. So it's a principle of locality, or a subjective view. So this is the line of the Cartesian space. So with the ramp we cut it here and took this, and here we make this kind of hyperbolic distortion of things. So now embedding that in a linear setup of all the parameters to train, the linear parameters to train, what you can imagine that we have a lot of these hyperbolic spheres, and their size, their position is varying on the plane. So this is what they're doing. Let's go here and train a new net. So we simply did the same thing, but we introduced a logistics sigmoid, kept the rest the same. So this is our network, and we train it. So this is getting better. If we put the graphics, then you see it's starting to fold. So it's getting non-linear here. It's able to fold because there are different views. So the sigmoid, if you look at here, so the sigmoid, there are 4 of them, 4 different perspectives. So if in the next level we, for example, increase the amount of dimensions in a. So now we increase the resolution. So we add more of these sigmoids. Train them. Get the graphics. Now it's perfect, and here we are, and we had been able to train this stuff. So whereas if you go for higher resolution in a linear way, in a linear setup without the sigmoid, even with increasing resolution, no effect. Yeah, and if you simply do it with the ramp here instead of logistic sigmoids, it gets similar results like the sigmoid. So therefore, this cut is it's taking a subjective view. So this binary distinction between 0 and 1 is a subjective view. This is the bit. It's a cut, and there we are with with the cut of Dedekind cut in mathematics, the manifolds for Riemann and so on. All this is implemented in the neural networks and has to be taken into account at the edge of the world. You're not part of the linearity of time. It's not working. In contrast to all rhetorics around neural networks to make it simple to understand. Thank you for watching and see you tomorrow.